Hello and welcome, everyone. My name is Lauren Harrington, and it is my great privilege to be the host of today's webinar. Joining us, we have a very special guest speaker, but before we dive into things, I do have a few quick housekeeping announcements which I would like to make. First, I'd like to point out a couple of bonus features which you have access to since we're running Zoom in webinar mode today. First, if you take a look down at the bottom of your screen, you should see a Q&A button. If you click on the Q&A button, you can type in questions for the presenter, and I highly recommend that you do just that. Don't worry, when you submit a question, it will not interrupt the speaker. Feel free to submit as many questions as you'd like at any point during the presentation. And after the presentation is over, we'll have a Q&A session where we'll try to answer as many of your questions as we can reasonably get to. Next to the Q&A button down at the bottom of your screen is a button labeled CC or Show Captions. That one will enable or disable Zoom's automatic captioning, which is a handy one to have in your toolkit. Sometimes it gets things right, sometimes it gets things very wrong. Okay, so now for a special announcement. Our 113th annual meeting is going to be held at the US Space and Rocket Center this November. It is less than 2 weeks away, which is a little bit intimidating for all those of us who are going to be presenting posters and giving talks. The deadline for registering for in-person attendance has already passed, but we still have remote registration open. It will close tomorrow though. So if you have been thinking about attending the annual meeting online so that you can still watch the talks, still view the posters, still enjoy the science, today is kind of your last chance. You need to go ahead and register for the meeting now, as soon as you can. We will be broadcasting all of the sessions on both Saturday and Sunday, which includes 2 of our keynote speakers and a whole slew of interesting science talks. If you'd like to see the schedule, you can visit our website, aavso.org/113. And on that page, we have an interactive schedule where you can view the titles of the talks that are coming up, click on them to see the abstract. I know that a lot of people are already signed up to attend both in person and remote, and I'm really looking forward to seeing all of you there. I would also like to make an announcement about our next webinar in this series. This one is not coming up next month this time. It's 2 months out. That's because next month we're having the big annual meeting with, 30 different presentations in it. So we figured we'd give you guys a little bit of a break. But in December, we're going to come back strong with a webinar by Bob King. And Bob King is going to be presenting on things I thought I'd never see. Stories from his long history as a visual observer. And he's going to be tying it all in with the art and practice of visual observing. It'll be a great webinar to attend if you're interested in visual observing at all, whether you are a beginner or whether you've been doing it for 50 years. And I really hope to see you all there. If you're curious about this webinar, maybe you'd like to read some more info written up by Bob, or you'd like to go ahead and register, we've got a QR code on the screen. That QR code should go to the registration page. And you can also visit our website, aavso.org/webinars. You'll find more information on that page. Today's webinar is generously sponsored by Boyce Astro. We would like to take a moment to thank and acknowledge them for their support. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. All right, now, remember I mentioned that joining us today, we have a very special guest speaker, a visual observer, an avid astrophotographer, and now a PhD student in the Center for Astrophysics at the University of Southern Queensland. His research focuses on planets and stars, from discovering new exoplanets to learning about the formation, evolution, and demographics of stars and their planetary systems. Lately, he's been working on a novel project which combines space-based photometry, binary studies, and classical variable star science in order to study systems which previously defied characterization. Now, I first heard about his work a couple of months ago when our speaker gave a stellar presentation during the 3rd TESS Science Conference at MIT. Not even 5 minutes into his talk, I made a note in my notebook. We have to get this in front of the AAVSO. And very luckily for us, he accepted our invitation in spite of a really unfortunate time zone difference. So it is with gratitude and great excitement that I welcome to this virtual stage Shishir Dholakia, here to offer us a glimpse at the cutting edge of research. Welcome, Shishir.
Thank you very much for that. I'll go ahead and share my screen. One thing that Lauren didn't mention is that I have been a visual astronomer since I was a little kid. But on one of those star parties that I was attending, it was actually an AAVSO astronomer by the name of Dave Majors who got me interested in variable star observing. And that slowly led into a pipeline that got me into research astronomy, which is where I'm at right now. And so I have the AAVSO to thank for my interest in research. And I'm honored to give this presentation here today. So yeah, I'll get into it. I'm going to be talking today about a kind of niche and interesting technique that we can use to map intermediate period binaries using pulsation timing variations. And I'll explain what that technique is. So that the title is originally wide binaries, but I think intermediate period binaries tends to be a slightly more accurate term, and we'll get to why exactly that is over the course of this talk. To start out with, I want to give you a bit of a background. And one of the things that I need to give you a background about is the Kepler mission. So I personally do study mostly exoplanets around stars all over the galaxy. And the most central mission for studying exoplanets is the Kepler mission. So the Kepler mission was launched in the late 2000s. It was designed to stare at an area of the sky about your palm, stretched out at arm's length. And it was supposed to stare at that region of the sky for its entire mission lifetime. And it did that with great success. It was monitoring the brightness of all of the stars in this region over here in Cygnus. And its goal was basically to try and take measurements of the brightness of all of the stars in this region over time. So what it was doing, of course, was the transit method. It's this technique where you monitor a star's brightness, and if it's being orbited by a companion, that companion can go in front of the star and block a little bit of the light from the star, causing a dip in brightness. And this dip in brightness is expected to be periodic because that companion is orbiting the star, and every time it orbits, you expect another dip in brightness. So this is called the transit method, and Kepler used it to great success. It discovered thousands upon thousands of exoplanets, various different kinds of variable stars as well, because it's the same kind of technique of monitoring the brightness over time, which you can use to identify variable stars as well. Unfortunately, the Kepler mission eventually ended up giving out. It wasn't able to point stably in one direction. And luckily for us, scientists were able to launch a new telescope right on time called the Transiting Exoplanet Survey Satellite. So the Transiting Exoplanet Survey Satellite decided to take a different strategy to observe the night sky. Rather than pointing at one tiny area of the sky for its entire life, the TESS mission is trying to map the entire sky. So it takes a scanning strategy. It's actually a rather small satellite. It's only maybe the size of like a trash can or a garbage can. And it basically looks at squares of the sky, and it tiles the entire sky over the course of a year. The drawback to this, of course, is that as it tiles the night sky, it has to do so over much shorter segments of time. So a sector for TESS observations is only 27 days, as opposed to the 5 years that Kepler was able to stare at the sky for. So this is one of the limitations of TESS, but there are ways to get around it. And some of the sky is observed for much longer than 27 days with TESS. So when you find a companion to a star, one of the first things that you should do is to try and obtain radial velocity follow-up. So the transit method, as I mentioned earlier, allows you to measure the dip in brightness as a companion crosses the face of its star. And the depth in brightness gives you something about the size of that object, because a larger object will block more light and therefore cause a deeper dip in brightness. So this radial velocity method is very complementary. It basically involves trying to discern the wobble of the host star as a companion is orbiting around it. And if you're familiar with the Doppler effect, it's kind of it's the same effect as when like an ambulance goes by and it's high pitched when it's going towards you, and the siren gets low pitched when it's going away from you. The same effect happens with light, because light is also a wave. So when a star is wobbling towards us, it's ever so slightly bluer. And when it wobbles away from us, it's ever so slightly redder. And so as a star wobbles due to the gravitational influence of something that's orbiting around it, we can discern this color shift in order to figure out what the mass of that companion object is. And so an object with more mass orbiting around this host star would tug on it more and therefore make it wobble more. And we discern that as larger color shifts. So the radial velocity method gives us the mass. The transit method gives us the size. These two techniques have been really complementary and really good for exoplanets, because we can understand the density of exoplanets using both of these techniques. But more broadly, the transit method and the radial velocity method are also used to identify binaries. There is a catch, however, to these two techniques, and they're outstandingly prolific. They've been used to identify uncountably many binaries and exoplanets at this point. But the drawback to these techniques is that they're both biased towards short period companions. So if you look at this diagram over here on the right, you can see that for the transit method, you kind of need the right line of sight in order to even observe a transit. If the inclination of the system is not aligned with us, with the Earth, the companion will never transit, and you'll never see this dip of brightness. And what's worse is you can see that if the companion gets farther and farther away from its host star, if it's in a wider orbit, the chance of it happening to cross in front of the face of that star gets much lower. And in fact, if you're mathematically inclined, this scales as the negative 2/3 of the period. And so for those of you who are mathematically inclined as well, the amount of the color shift, what's the so-called radial velocity semi-amplitude, scales as period to the negative 1/3 power as well. So both of these techniques are basically biased towards short period exoplanets and companions. So we would, of course, like a technique to access something a little bit longer period. So why is that period range special? When I say intermediate period, I mean something from like 10 to like 1,000 days. And why is this period range particularly special? It's because there are multiple objects in that period range that are exotic and cataclysmic and really interesting if you're either studying binaries or if you're studying other kinds of objects. First of all, we have post-mass transfer binaries. And I'm going to get to this later in this talk, but this is a really exotic kind of object that's really interesting. For those of you who know what type 1a supernovae are, they're basically these supernovae that occur when you have two stars orbiting each other. One star kind of donates mass to the other, and there's this critical limit at which, when this secondary star gains enough mass, it collapses and it goes supernova. And the amazing thing about these type 1a supernovae are that they all go off at exactly the same brightness, no matter where they are in the universe, which means that we can use them as standard candles. So standard candles are objects that we can use in order to determine distances in the universe, and they form the bedrock for what we know about our universe, because we can use them to measure distances. It's very difficult to measure distances otherwise, and type 1a supernovae are really, really important for this reason. In fact, type 1a supernovae are a big reason for why we know that the universe is accelerating in its expansion. So type 1a supernovae are extraordinarily impactful to cosmology, And the progenitors for these objects happen to be intermediate period binaries as well. So we want to try and identify them. And of course, we have brown dwarfs and exoplanets. And particularly these brown dwarfs and exoplanets, if they're in the intermediate period range, could well be orbiting in the habitable zones of their host star. And as an exoplanet astronomer, that's particularly exciting to me as well. So I'm going to walk you through this figure really quickly. It's a little bit complicated, but basically on the y-axis, we have the mass ratio. So this is the host star's mass divided by the companion's mass. So that's to say, basically, down here, you have the systems where the mass difference is really large. Planets, for example, consist of something that's really low mass and really high mass. So you expect planets to hang around here. And then at the highest mass ratios, you have stuff that are about equal in mass. And this red region over here are the eclipsing binaries. So these are the objects that transit, basically, these binaries where they actually cross in front of the face of their host star. And many of you are familiar with the eclipsing binaries if you've done variable star observation in the past. They're very exciting objects because you can sometimes see them dip in brightness. But of course, these binaries tend not to eclipse, as I mentioned earlier, the longer period they are. So like around here, you tend not to see eclipsing binaries anymore. And that would be, so this is a log scaled plot, but this is basically saying that this is somewhere around like 80 days or so, 70 days or so, you stop seeing very many eclipsing binaries. This orange region over here are the radial velocity binaries. So this region is basically when you have two objects of similar mass, you might be able to detect the radial velocity motion. And at short periods, you can usually detect the radial velocity motion too. But this region over here, it's very difficult to access with radial velocity. And finally, this blue region here is called interferometry. It's basically a technique that you can use to directly image binaries. So if you can actually resolve them as separate, that's kind of the easiest way to figure out that you're dealing with a binary, because you can see the two individual stars. But of course, this only really works for stars that are bright enough. So you need both the stars to be bright enough to do this. And you need to really have the longer orbital periods. You need to have wider separations, otherwise you'll never be able to resolve them as separate. All of these techniques kind of have a gap in between them. So I'm going to quickly talk about the bedrock of this technique, and that is the delta Scuti variable. So some of you are familiar with delta Scutis, but I'll quickly explain what they are. These are A-type stars. So they're slightly hotter than the sun. They're maybe like 1.5 to 2 times the mass of the sun, and a little bit hotter than the sun. And they're really special because they pulsate at multiple periods between about 30 minutes to 5 hours, but they're extraordinarily regular. This is a real TESS light curve of a delta Scuti star. And you can see how sinusoidal, how perfect this light curve is, right? This purple data is binned, and the gray data is unbinned. And you can see that you can basically time your clock to this. It is extraordinarily precise. And because they have such short periods, between 30 minutes to 5 hours, they really do make really good astrophysical clocks. And so the idea of the pulsation timing variation technique is that we can leverage this clock-like pulsation in order to identify unseen companions to these delta Scuti stars. So over here in blue, we have a delta Scuti star. And let's say it's being orbited by a companion, this red companion over here. As the companion orbits, this delta Scuti star will wobble a little bit. And it'll actually wobble far away and then near to the observer as it goes through its orbit. Oh, sorry. So when it's far away from its orbit at time 1, the pulsations take longer to reach the observer because the star is physically farther away, and light has to take time in order to travel to our eyes. So if the star is, say, 20 light seconds further away, then the pulsations will arrive 20 seconds later. And then as the star wobbles towards the Earth, it might get 20 light seconds closer to us. The pulsations will arrive slightly early, and we'll detect that as the pulsation phase is slightly early. And so if you plot when the pulsations are arriving over time, you'll notice that for some of these delta Scutis, the ones that might be orbited by an unseen companion, you notice that the pulsations start to arrive early and then they start to arrive late in this very neat sinusoidal pattern. So this sine wave isn't to be confused with the actual graph of brightness over time. Rather, this is the pulsation timing, and we're noticing that the pulsation timing is varying. And of course, the 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 period of this pulsation timing, the period of the sine wave, gives you the orbital period of the binary system. And the amount of pulsation timing variation gives you the mass of the companion. And so this allows you to gain some really interesting insight into the actual characteristics of the system that you're looking at. Even though you can't even see the companion, we can infer its presence with this method of pulsation timing variations. So this technique hasn't actually been used as often as you might expect, but it's extraordinarily interesting, I think, because you can kind of get everything that you get from radial velocity for free, because telescopes like Kepler and TESS are observing large parts of the sky, are collecting these extraordinarily precise brightness measurements, and we can kind of use those in order to make discoveries and identify the orbits of these binaries, kind of for free. We don't really have to go out and do anything extra in order to get this data. So I mentioned earlier all of the different things that we want to do in this intermediate period regime. And PTVs are especially sensitive to this area, which makes them really exciting. And even more exciting is with TESS, because TESS is looking at the entire sky, we can obtain orbits for binary companions to some of the brightest stars in the sky. So we basically decided to go into the TESS data, try and find as many delta Scutis as we could in all of the TESS data. So we took 1,416 light curves, each of a unique delta Scuti star, with enough data that we can actually use this technique. So out of that, we were able to distill it to a sample of 1,161 true delta Scutis that we actually think are delta Scutis and not some other kind of pulsator or some other variable star. So for each of those delta Scutis, we've divided the light curve up into 5-day windows. And in each of those 5-day windows, we estimated the timing of the pulsations. And from that, the binaries or the delta Scutis that seem to have pulsation timing variations, we can say that they're possibly binaries. And for the possible binaries, I created this computational model. So for those of you who are familiar with programming, there's this code package called JAX, which is very nice and allows you to do some things that were kind of previously unprecedented. And what I can do with this JAX-based model is basically I can take all of the different kinds of binaries that could be, right? And I can predict what the light curve of those binaries would look like. And I can directly fit it onto the light curve that we see. So whichever one fits the best, that's the one that is the real light curve of this system. And we can use this in order to figure out the mass, the eccentricities, the orbital periods, and all of the different parameters of this binary system. So this is what's called a forward model. And you're welcome to ask me more questions about this methodology, but because not everyone has a computational background here, I'll kind of skive over this part. But basically, this technique allows you to get to take a light curve and obtain all of the parameters, all of the characteristics of these binaries robustly and quickly. So out of this whole technique, we discovered 53 new binaries. And so here are the pulsation timing variations of some of them. And you can see that they're quite diverse, right? You have some that are really sinusoidal. They look almost like a perfect sine wave. And that basically means that the orbit is super circular, right? Very, very, very close to a perfect circle. And then for these, they don't look like perfect sine waves. They look like slightly different shapes. And this is because they have some degree of eccentricity. So their orbits are actually ellipses. There's even a really cool object here at the bottom left that's what we call a PB2 system. So this is where you have two delta Scutis orbiting around each other. And so initially, this kind of can seem like a hopeless mess because you have the pulsations from each of these systems. And when one system is close, the other system is far. So some of the pulsations are arriving late and some of them are arriving early. But with this program, I'm basically able to disambiguate those two different pulsation patterns. And you can see the blue pulsation pattern is one of the stars, and the purple pulsation pattern is the other star. And so when one of the pulsations are arriving early, the others are arriving late, and vice versa. So this is called a PB2 system, and we can do some cool things with these PB2 systems that make them particularly interesting. So we set this one aside. There's 49 more of these binaries as well. They're all really cool and interesting. And the full data is in the paper if you guys are curious about it. I'll mention that a little bit later. So if we look at the periods of the different binaries that we found with this technique, what do they look like? So honestly, they span the whole range of periods from all the way down to like something around 20 days to almost 1,000 days. And so these are kind of fully within the intermediate period range that we were hoping for. So this is very exciting. For some of the systems, the period is just too long for us to be able to get a really confident solution. So those are the ones in gray over here. So we're waiting for more test data to be able to get to really nail the periods on these ones. But with additional data, we will be able to figure out the exact period and be able to nail down the system characteristics for these. So there's one target in our sample, one star in our sample that's particularly exciting. Earlier this year, we had a wonderful display of aurora around the world. And in Queensland, in Australia, where I live currently, aurora is exceptionally rare. It would be like seeing aurora in San Diego around if you're from the US. So we didn't really expect to see it, but we decided to go out and try to see whether we could spot any. And to our surprise, we were actually very clearly able to see it both on camera and to our naked eye. One thing that was really cool when I was going through the footage, though, I realized that right in the middle of the aurora is one of the targets in our sample, Alpha Pictoris. It's one of the brightest stars in the night sky. It was actually not known to be a delta Scuti until the TESS mission. But the TESS mission identified that it was very clearly a delta Scuti. In fact, the light curve that I showed earlier, oh, sorry, looks like it stopped my screen sharing, but I will go ahead and get that back up. The light curve that I showed you earlier is actually that of Alpha Pictoris. So if I go back and show you that light curve real quick. So this is the light curve. This is one section of the light curve of Alpha Pictoris. And so you can see it's really, really clearly a delta Scuti, but it was not known to be a delta Scuti before the TESS mission, which is quite extraordinary. So for Alpha Pictoris specifically, it's one of the stars that we found a possible binary around. Because it's so bright and because it's so interesting, we wanted to do a special kind of analysis for this. So what we ended up getting from Alpha Pictoris is this pattern of pulsation timing variations. And you can see it's really clear. It really clearly seems to show a binary. So the full history of Alpha Pictoris was earlier, about a decade ago or so, a telescope identified a hint of X-rays coming from Alpha Pictoris. And this seemed to suggest that Alpha Pictoris was a binary because A-type stars, the kind of stars that delta Scutis tend to be, don't usually emit X-rays. So that was already a hint. The Hipparcos mission, which looks at the position of stars very, very carefully, also detected a bit of a deflection but it wasn't able to identify the orbit of the companion conclusively. And so there was these suggestions that Alpha Pictoris might be being orbited by a binary, but we really didn't have the actual orbit for the binary, and we didn't know what the binary would look like. So with the pulsation timing, we were actually able to nail the orbit for the first time. And along with the pulsation timing, we decided to also fit that astrometric data, which is the very precise data for the position of the star. And so this is literally resolving the wobble of the star due to the influence of the companion. So on the y-axis is the declination, on the x-axis is the right ascension. And so this is because of the pulsation timing data, we were able to very clearly fit the astrometry data as well and get a very clear orbit for Alpha Pictoris. So it turns out Alpha Pictoris is being orbited by a star that's actually quite similar to our sun, almost exactly one solar mass, we think. And it's being orbited once every about 1,300 days or so. And it's moderately eccentric. So this orbit looks really oval-shaped, both because the orbit is slightly eccentric, or around 0.3 eccentricity, but also because the orbit is inclined relative to the Earth, and so it looks oval-shaped as well because of that. And so Alpha Pictoris has been particularly interesting. It's one of the brightest stars in the night sky, and for the first time, we're able to get the orbit of Alpha Pictoris. Another thing that we can do is we can look at the galactic kinematics. So one thing I should mention is that our TESS sample of pulsation timing variation binaries preceded another work which did this with Kepler, which found a bunch of binaries as well. And this Kepler sample has been a really useful comparison throughout our work. So we can sort of compare and contrast the TESS pulsation timing binaries, which are typically brighter and all over the sky, with the Kepler binaries, which are a little bit fainter in one area of the sky, but because Kepler was staring for 5 years, it was able to get some slightly longer period binaries as well. So one thing we could do is plot something called a tumor diagram. And this is a bit of a specific detail, but basically you can think of this as plotting the velocity of the stars through a galaxy. The idea here is stars that are young tend to be born with very little motion in the galaxy. And so they tend to hang around near the origin of these plots, near 0, 0. But as stars age, they tend to slowly drift away in this plot. And you'll notice that the oldest stars in our galaxy are hanging out way outside. So this dotted line over here kind of guides your eye on whether stars are old or young. And I should point out that so -50 is over here in this plot, and -50 is over here in this plot. And so stars outside this dotted line, we tend to think of as pretty old. I'll also draw your attention to a detail that I mentioned earlier, which is that A-type stars tend to be, or are always more massive than our sun. And therefore, they have main sequence lifetimes that are significantly shorter than our sun's. So our sun will live around 10 billion years, we think. But A or F type stars, the Delta Scuti stars, in other words, will only last maybe 2 billion years or so. One thing we found when we plotted the galactic kinematics of our sample was that these stars, some of these stars, maybe a handful of these stars, were consistent with much older populations. So rather than being 2 billion years old, which is what we'd expect for Delta Scuti, we found that these are more consistent with something that's older than 5 billion years old. So we decided to look at the Kepler sample as well, and we found something similar. A handful of these stars are actually much, much older than they should be. So what's going on here? How is it possible that Delta Scuti stars can be something like 5 to 10 billion years old when they should only be living for 2 billion years? So what we think is going on here is that these are blue stragglers. These are stars that are anomalously old. And what basically has happened is that what we're looking at is a star that's now a Delta Scuti, an A-type star, and it's being orbited by an invisible orbital companion. But if you roll back the time, originally the system looked like a smaller star and a much bigger star, and that bigger star actually reached the end of its lifetime and it blew up, it became a red giant star. And when it became a red giant star, it started to donate the mass onto this cooler star. And that cooler star started to basically eat it up, become slightly larger, and actually became an A or F type star after the fact. And so after this whole system has basically lived an entire lifetime, this secondary star has donated a bunch of its mass. It's rejuvenated its companion. The companion has become a delta Scuti, maybe something like 2 or 3 billion years into its lifetime. And this companion, this invisible companion that we see now, is the dead remnant of that original star. It's called a white dwarf. And so these systems are particularly exciting. We think that our hypothesis, of course, is that these delta Scutis are being orbited by a binary, and we think that binary is actually a white dwarf. And this is a testable hypothesis. We can go out, we can try to observe. Some of these can be observed interferometrically. Some of these can be observed with radial velocity, and with other techniques that can allow us to confirm that the companion is indeed a white dwarf. And so we're currently attempting to do this, and stay tuned for more news about that. So there's lots of things that we can do in the future. Additional years of test data will basically just increase the yield overall, and that'll allow us to access longer orbital periods and excitingly for me, lower mass companions. So right now we're just getting below the substellar limit. So we're just at the point where we can start to detect things that are brown dwarfs. And with more data, I'm quite confident that we can detect brown dwarfs and even exoplanets in the future of TESS. There's also this thing called Gaia that's releasing its 4th data release sometime next year, or maybe we're not quite sure when it's coming out, but it's planned to be quite imminent. Gaia is basically is like a much better version of Hipparchus. So you saw that for Alpha Pictoris, I was able to look at the actual orbit of Alpha Pictoris's companion with the Hipparchus astrometry. Gaia is doing this for many more stars than just the brightest stars in the night sky. So in Gaia DR4, we actually expect almost all of our binaries to be in this catalog. And what's exciting about this is like Alpha Pictoris is the first time anyone has ever tried using the pulsation timing technique along with the astrometry technique. And it was fantastic. It was such a synergy between these two techniques, because one of the techniques gives us the inclination of the orbit, the other technique gives us the eccentricity and all of the orbital parameters very precisely. And so this is very exciting for the future of Gaia, because we can look at all of the stars in our sample with Gaia as well. One thing that's kind of like an open-ended project idea that I want to bring to you guys, and please let me know if any of you are interested in this or are interested in trying something like this. I, of course, started out with research astronomy by taking out my DSLR camera and taking images of Beta Lyra, Delta Cephi, and some other like variable stars. Eventually, even some exoplanets, HD1 and 9733b. So I know that it's quite possible to do accurate photometry in your backyard with a CCD or a CMOS or even a DSLR. The thing that TESS lacks, or that any kind of space mission may lack, is that we don't yet have longevity. So these telescopes will either run out of fuel, or they'll run out of funding, or they'll run out of something else, maybe 5 years into their lifetime, that makes it very difficult for us to do very long-term monitoring. But that's, of course, where amateurs excel, because we can basically take an arbitrary length of data, and we can even go back to those Kepler objects, and we can observe those Kepler objects. We can look at the TESS objects, and we can observe them whenever we want to. So the idea here is basically, if we can monitor some of the Kepler objects or the TESS objects and identify the light curve, and we can identify the pulsation patterns, we can try to see how accurately we can time from the ground the arrival of those pulsations. And so Kepler happened almost, it's more than a decade ago now. So if we go back and observe those Kepler targets, we might actually be able to detect binaries that were only tentative with Kepler. And there's a handful of those binaries that I think we can actually identify quite confidently from the ground with an amateur setup. So if anyone's interested in that, feel free to reach out to me. And this paper is now accepted. It's coming out to archive on Monday. And this is kind of just like a summary of all the things that I've mentioned here. Feel free to ask me anything about like long period transiting planets, which is my bread and butter, or pulsation timing binaries, or anything else that I might have mentioned over the course of this talk. Thank you.
Wow, excellent presentation. Thanks so much, Shishir. That's so exciting. So we have had a bunch of questions coming into the Q&A. I'm going to jump the queue slightly and address the really exciting DSLR observing project that you just talked about. Are you aware of the AAVSO's observing campaign system?
Vaguely aware of it. It's been a while since I've looked at it, but I think I have contributed observations to that a long time ago.
Cool, cool. All right. So if you're interested, we can talk offline later about this, but if you're interested, I can put you in contact with the person who's in charge of the observing campaigns, and we can write up a formal announcement so that more of our observers than just those who are in attendance to today's webinar will get your list of targets that you're interested in, and you can share with them what kind of data you're interested in seeing. So that's something we can talk about a little bit later if you'd like.
Yeah, I love that. I think what might be necessary first is a little pilot study, basically to look at the feasibility of doing this from the ground. And it has been done from the ground before, but to look at the feasibility of doing it from like truly amateur setups to see whether we have the photometric precision or not. But yeah, that's definitely something I'm very excited about.
Smart. Okay, so diving right into the questions. We have a great one here from Calais Talk. So Calais Talk is asking about your methodology for estimating the phase of the pulsators in these binaries. Given that delta Scutis pulsation periods are typically about 30 minutes to 5 hours, in that very short range, what was the motivation behind choosing a 5-day window to bin and estimate phase? Why that long?
That's a great question. And it basically comes down to the accuracy with which you can time these pulsations is not just about like one pulsation cycle. It's not just about how accurate your clock is. It's also it's limited by how good your photometric precision is. So as you can see, the purple dots here are really precise, but you need them to be really, really precise in order to make these measurements on the scale of seconds, because you can see here, like this is the scale on the axis over here is in days, but we're trying to detect variations in this pulsation phase on the scale of seconds in order to detect the binaries that we're talking about. And so 5 days gives us both enough data that we can get good photometric precision, as well as good timing precision, so that we don't miss the shortest period binaries. That was kind of the balance that we looked at there. But apart from so that was kind of just our way of shortlisting the binaries. The technique that I told you about, which is the forward modeling technique, actually doesn't have any like window size. It is like infinitely precise in that like we can basically get arbitrarily short period binaries if they were to exist, or we can do arbitrarily precise measurements of the orbital period or the pulsation phase. That's a great question.
Yeah, cool. Okay. And there was a kind of a follow-up thing also from Clay Talk, which is when you did this binning to do this preliminary sort of the binaries with your 5-day windows, in order to get the phase, were you generating a periodogram and then using the period differences to infer the PTVs, or were you more directly measuring, like the peak moments of peak flux, or how were you doing that?
That's another great question. Yeah, so initially we have to identify our delta scutis in the first place. So yes, we do use a periodogram. I have a hidden slide over here for you. This is the top is a light curve of Alpha Pictoris. In the second plot is the actual periodogram. So you can see that the highest peak in this periodogram is about one sixth or 1 out of 6 inverse days, which is somewhere around 4 hours or so. And what we do from there is we basically have a sine wave at that period that we take to the light curve, right? And we can fit the pulsation phase for each of those 5-day windows. And each of these dots over here represents one of those, the timing measurement in each of those 5-day windows. And so as I mentioned earlier, delta scutis are multi-periodic. So they have many peaks in the periodogram. And that's why I have these color coded by which peak we're looking at, right? So the purple arrow points to this peak, and the purple data points reflect the measurements made with this periodogram peak, and the orange is for the orange peak, and so on. And so from that we can figure out that there's this pulsation timing variation, as you can see here, that's occurring on all of the peaks, and all of them are agreeing. And that's a really good sign that this is actually a real effect, because all of these peaks have the exact same phase delays that we're observing. So that's kind of the nuts and bolts of how we go about this.
Cool. Thank you for sharing.
Yeah, great question again.
So our next question here comes from Paula Scoti, who says, I was somewhat surprised to see the relatively low number, only 50 out of 1,000 or so binaries that you found. Is this low number consistent with the expectations for A-type stars?
That's another excellent question. So it is not. We do have a particularly small yield. There's something in this line of work that we call an occurrence rate statistics, and a completeness correction, which is basically based on how many we find, what our yield is. Can we try and correct this to figure out how many are actually out there, right? And people have tried this. We kind of made an attempt at it, but it's very difficult with TESS. And that's because, actually, I'll go back to this data that I showed you earlier, because it's real data. You can see that there's a lot of gaps in this data. So these gaps in the data make it really hard to identify certain periods of binaries. And so if there are binaries at particular periods, this is actually one of the better sets of data that we have. There's some data out there with many, many more gaps, and much more gap than there is data for TESS. So that's kind of the reason why we have a reasonably low yield compared to what you might expect. But part of that is also just that not every A-type star has a binary at an intermediate period range. It's not, I think the occurrence rate statistics is somewhere between 10 and 50%. So it is not entirely like certain that you're going to have a binary around every delta scuti that you look around. And the rest of that is because TESS has gaps that make it very difficult to identify some of those binaries. So TESS will fill in those gaps over time, and we'll be able to get confident or higher yields for the systems that we're looking at.
Okay, see, that makes a lot of sense. And it sounds like in the meantime, until we do have continuous space-based photometry eventually someday, that's a good case for having amateur follow-up when you can have people stationed all around the world and getting kind of more of a continuous baseline. Speaking of that, we had a couple of questions of people who are from people who are interested in helping with this sort of pilot study. First, and probably most importantly, how can these people reach you if they would like to participate?
Yeah, so I have, someone says my email is not correct. Let's see if I can fix that for you. Okay, I will go ahead and put another email in the chat that you can use to reach me, if that is bouncing. And you're welcome to reach out to me on there and ask me questions. I will say that a pilot study like this will probably require slightly more advanced equipment for starters. We can then think about working down to more like uh, DSLR type equipment. But I think for starters, what we'll need is someone who has some kind of like backyard observatory type situation that can do reasonably frequent monitoring with a reasonably large aperture. And then we'll see if we can work it down to even DSLRs. For stars like Alpha Pictoris, we might even be able to do like more humble equipment. But for starters, I think for a pilot study, we might need larger setups to do this kind of thing.
That makes sense. I saw that Grant in attendance had said that he thinks that people with the larger CCD setups should be able to tackle that kind of thing. So it sounds like that's what you're saying as well. Excellent. Okay, so and then a question from Pat Boyce while we're taking questions along this topic. What sort of clock accuracy requirements are there for doing this project? And also, what sort of cadence should we target?
Yeah, the clock accuracy shouldn't be a limitation, actually. If you can time within like sub-seconds, which is um, probably more than most people can, or probably more than adequate for most of these purposes, because the more practical limit will tend to be the limit of your photometric precision. So no spectroscopy is required. The nice thing about this is you can do this without any kind of, you can do this in broadband photometry. All you need is a camera and a telescope, and you can do photometry with that. So this is just a photometric technique. That's why it's kind of like getting radar velocities for free. Yeah, so you don't need a particularly precise clock in order to do this. Like a standard clock on a CCD should be more than enough.
Got it. Okay, thank you. All right, one more question on observational techniques for studying these kind of systems from the ground. Yogesh Chavan is curious whether normal CCD photometry is the way to go, or differential photometry. So
yeah, you could do either. Yeah, I would say differential photometry is the ideal, because you don't really need an absolute measurement for this technique. What you want to identify is the pattern in pulsation, so that you can identify the phase of that sine wave, and that'll allow you to get the measurement that you need. You don't really need an absolute measurement. So yeah, differential photometry is the way to go.
thank you. Okay, going back now to a couple of the questions about the science. So we have a question from Soonwook Kim saying, you'd mentioned that delta Scooties don't emit X-rays. Is it that they really have no X-ray flux at all, or is it more that we currently don't have the ability to detect an X-ray flux that weak, but they have some that we might be able to detect in the future?
Yeah, if I guess I can go a little bit into the physics about this. There's two kinds of radiation that you tend to get from stars. One is called black body radiation. So that's the radiation that you get from just an object that's thermally radiating away. So, for example, humans radiate in the infrared, which is why if you take an infrared camera and point it at a human, you get like this bright spot, right? And stars tend to radiate in the visible range of the spectrum in black body radiation. If you go like to farther and farther wavelengths down all the way to X-ray, that black body emission starts to dip very precipitously. And so even A-type stars, which are pretty hot, have little to no black body radiation in the X-ray. So you really need something else to be generating that X-ray emission. We think that the convective photospheres of cooler stars can generate this kind of X-ray emission. So K-type stars or G-type stars, like for example, our sun has this granulation, and that something about the way that the charges move through that convective pattern can produce X-ray emission that you can detect with X-ray telescopes. And so that's kind of the tip off that we're dealing with some other object that we can't necessarily see directly, because delta Scooties are either fully convective, or their outsides are completely convective. Sorry, are completely radiative, which means there's no material kind of roiling around. and therefore we don't expect them to be emitting very strongly in the X-ray.
Interesting.
That's a great question. Mm-hmm.
Thanks for that explanation. Our next question comes from Thomas Lawn, who asks, why are older stars faster?
Are older stars faster in terms of like the pulsation period or the...
I think that was in reference to the galactic kinematics diagrams that you were showing earlier.
Yes, the tumor diagrams. Yeah, that's a great question as well. The reason, oh, let me quickly share the screen. The reason why older stars tend to be faster is because stars are born at the velocity of the nebula that they form in, right? And that nebula tends to be moving along with the galaxy. So this is a plot of the motion relative to the surroundings of the galaxy, right? It's called the local standard of rest. But as stars age, they tend to encounter other stars, and like they kind of get kicked by those other stars, and like they have a lot of different encounters, and over like billions of years, that actually causes them to start moving in some random direction relative to the galaxy. So this can't really be used to confidently age a single star, but if you have multiple stars, you can kind of see that like statistically, it's unlikely for all of those stars to be moving much faster than you'd expect for a population that's super young. And so you can kind of use this to statistically say that stars that are moving faster relative to the local standard of rest have to be older because they've undergone these interactions and collisions. We have other ways of confirming that, yeah, indeed, stars that are further out on this diagram that are moving faster relative to the galaxy tend to be older.
Very
So
interesting.
this kind of study was definitely made possible by the Gaia mission. So the Gaia data release 3 has provided really, really precise kinematics for a bunch of different stars in our galaxy, including all of the different stars in our sample. And so with Gaia, we were for the first time able to do this kind of study and actually look at the ages of these stars. And it's one of the very few, if not only, identifications of blue stragglers that are just scattered throughout the galaxy. Usually you need a special situation like for them to be in a cluster or something in order to be able to detect blue stragglers. But with this kind of study, we can identify possible blue stragglers just out in the galaxy.
Cool. All right. So, highly related question.
Mhm.
Can you explain again how exactly you determined the age of the blue straggler stars?
Yeah. So we haven't really determined a concrete age for the stars in our test sample. We can just say that they look like they're older than 2 billion years because they're moving relative to the galaxy. They're moving faster than we expect a star of 2 billion years to be moving. For the Kepler sample, what we actually did was we were able to put a quantitative probability on it. So we think that there's two populations of stars in our galaxy. There's stars in the thin disk, and there's stars in the thick disk. The stars in the thick disk tend to be almost 10 billion years old. They have to be that old, basically, because that stellar population formed 10 billion years ago. And so when you plot a bunch of stars on a diagram like this, you'll actually see two populations emerge. One stars kind of scattered throughout the diagram, very far from zero. Those are stars that are 10 billion years old. They have some different properties like super low metallicities and stuff that allow us to identify them as part of this distinct population. And then we have thin disk stars, which constitute most of the stars that we see in our local neighborhood. And those are stars that are much closer to the origin. And for the Kepler stars, we're actually able to identify a handful of stars that are very consistent with membership in the thick disk. So these are stars that we know probabilistically have to be something like 10 billion years old. And so for the Kepler sample, we were actually able to say that these stars are very, very likely to be way, way older than you expect a delta Scuti to ever be.
Great, thank you. Very thorough explanation. Appreciate it.
Yeah, great
So,
question.
next question. This one comes from Yogesh Chavan, who is asking if this technique for studying intermediate period binaries would be applicable to stars with many companions, for example, a star with 3 or 4 exoplanets?
Mhm. That's an excellent question. I would say exoplanets is still like we're still working our way up to getting exoplanet sensitivity. There was one system that was claimed to be an exoplanet in Kepler. It turned out to be a binary star system from further observation. So this technique has yet to determine conclusively discover an exoplanet. But I think that we're right on the horizon of being able to do that. But multiple exoplanet systems are even harder than a single exoplanet. So we'll leave that aside for now. But the question about detecting more than one companion is an excellent one. I should actually probably mention something really interesting about Alpha Pictoris, which is that there have been spectroscopic measurements of the companion of Alpha Pictoris that place the companion's mass at something around 0.8 or 0.9 solar masses. And one thing that was we found a mass for the companion that's suspiciously higher than that. So it's not like conclusive, but it is intriguing. And my personal speculation is that the binary of Alpha Pictoris might actually be itself a double star, a binary, and that would explain the lower luminosity of the companion, and really well. And it would also like explain why we're not able to detect the companion as being as spectroscopically massive as we expect as dynamically. So you can kind of see with this system how we can infer not just one star, but even multiple star companions if they exist. The other thing is if you have multiple, like what you call a hierarchical system, like one companion orbiting closer and another companion orbiting faster, you would actually see something like another pulsation timing variation pattern in this. So like this is the large pulsation timing pattern, and then you'd see a second small pulsation timing pattern. So this is actually something that we intend on looking for more thoroughly, but we haven't identified any clear candidates of this yet. But we do expect them to be in our sample.
Whoa, cool. All right.
That's a great question. Mm-hmm.
Yeah. Okay, so speaking of Alpha Pictoris, we had a question
Mm-hmm.
submitted by Grant Foster asking what was the mass ratio that you had found while studying Alpha Pictoris?
Yeah, if I remember correctly, the mass ratio is something like 0.61 or so. So the host star is somewhere around 1.6 solar masses, and the companion is about like one solar mass or so.
Right. Thanks. All right. Next question here. This is actually related to the diagram that you were showing of Alpha Pictoris with the Hipparcos astrometry.
Mm-hmm.
What do those white connecting lines on the plot mean?
Yeah, it's a great question. It has to do with how exactly Hipparcos conducts its observations. So, like the resolution, these are called astrometers. They do really sensitive measurements of position. The caveat is they measure the position really sensitively only in one direction. That's called the scan angle, and that's what's being plotted by these lines. It's the angle that we actually have a sensitive measurement in. 90 degrees to that angle, we actually don't have a very good measurement at all. And so what I'm plotting here is not just the measurements, but also what direction those measurements are actually sensitive in. So together with all of the measurements compiled, we can come up with a much better idea of what the orbit is. And of course, the pulsation timing data is what allowed us to make this unique measurement of the orbit.
Right. Cool, thanks.
Mm-hmm.
Okay. We're getting down to just the last couple of questions here. This next one is from Mark Copper, who asked about the maximum period limit of 1,000 days. Is that a hard limit? If so, why is it a hard limit? And can you expect that to increase in the future as you get more data?
Yeah, absolutely. That is the thing that I'm really excited about. It's not a hard limit. It's a limit that's set by the fact that TESS has only been in the sky for a certain amount of time. So we're actually coming up on year 6, but this analysis did only looked at 4 years of photometry, and for Alpha Pictoris specifically, we included a little bit more up to year 6 of the data. And so this means that we can only really detect things with a little bit shorter orbital periods than that baseline of photometry that we have. And so that tends to be about 1,000 days. But there's definitely longer orbital period binaries, and this technique is actually preferentially sensitive to longer period binaries. So as we are more sensitive to things that are further out than 1,000-day orbital periods, we'll also be more sensitive to things that are less massive. So as I mentioned earlier, we're right at the point where we can detect like the lowest mass M dwarfs. And so if we're able to detect things that are, instead of 1,000 days, maybe 1,500 or 2,000-day orbital periods, we'll be sensitive to brown dwarfs and exoplanets. So that's super exciting in the future of TESS.
Wonderful. Thank you.
Mhm.
Okay. So I think that that is the last of our questions that is not directly related to your proposed pilot project. So if you'd like to offer a reminder while I'm pulling up our closing slides, if you'd like to remind the audience about how they can get in touch with you and why they should, then feel free to do that.
Yeah, for sure. Yeah. I've put my email address in the chat. I'm very happy to take any questions on there. So for the pilot study specifically, I'm looking for probably someone who has like a slightly more, let's say, something larger than an 8-inch telescope, probably in an observatory, because we need something that can monitor for longer, with a CCD or CMOS type detector, and then we'll go from there. So again, here's my email address in the chat.
Okay, perfect.
Yeah.
Just actually, it looks like it may have only sent to me. I think that's the default setting for Zoom chat.
Oh,
So if you want to set that so that it's visible to everyone.
Cool. Okay, that makes sense.
Alrighty. So before I get into the closing announcements, I'd just like to say thank you, Shishir, so much for leading this wonderful session today. It's been really great to have you here to share your time and knowledge with us, despite the extremely obnoxious time in your local time zone. So thank you.
Thank you so much for having me. It was really great.
Yeah. Now, before we close out, I would like to express our sincere gratitude to our 2024 series sponsor, Voice Astro. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Now, as a reminder, remote registration for our 113th annual meeting is closing tomorrow. So if you are interested in getting in on 2 days jam-packed with science talks and seeing the record number of posters which we had submitted this year for some reason, it's like 350% of the number of submissions we got last year, then feel free to visit our website at aavso.org/113, and there you will find instructions for registering to attend virtually. It's much less expensive to do so that way than traveling to Huntsville yourself. And we will do our best to make sure that you feel like you're a part of the experience right there with us at the US Space and Rocket Center. We've been talking, the staff has been talking about what are all of the best ways that we can engage our remote attendees this year, make sure that you guys get a chance to ask questions to presenters and generally participate fully. So I hope that I will be seeing many of you there, both in person and online. And remember, if you are one of the people who has signed up to give a presentation or present a poster, the deadlines for those for submitting your files for those to make sure that everything is prepared in time are coming up quick. So that's everything I have to say about that. See you guys at the meeting. All right, and another quick reminder, after the annual meeting next month, we are going to have a webinar at the very beginning of December, December 7th. Our speaker for that webinar is Bob King of amateur astronomy fame, and he'll be giving a presentation titled Things I Thought I'd Never See. It'll be sort of a walk through history of what it's like to be a top-notch visual observer, and I'll be tying it all back into the art and the practice of visual observing. This is a presentation that I can honestly recommend to people of literally any skill level. If you are a beginner, you don't really even know what variable stars are, except for after watching this presentation, you're now an expert on intermediate period binaries, so congratulations. But if you're a beginner otherwise, show up, you will learn so much. If you've been doing this for 50 years, show up. It's going to be immensely satisfying to hear Bob King presenting on his astronomical journey over the years. So if you're interested in registering, you can scan that QR code, which is on this slide. You can also visit our website at aavso.org/webinars. And on there, you'll find some more information about the webinar itself, as well as the registration link. And now for a special announcement. To those of you who are out there in the audience today, wherever you are in the world, I would just like to say thank you. It is your support and your engagement in all of our programs which allows us to keep growing, keep educating, and keep making an impact on variable star science. So thank you. We couldn't do it without you, and we're so grateful for your support. Now, today's broadcast has been recorded, so if you would like to go back and reference the recording or share it excitedly with all your friends, I would not blame you, you can find it on our Facebook page, where it will be automatically uploaded just as soon as I click the stop webinar button in a minute or two. Pretty soon, we'll also upload it to our YouTube channel, where it will join an enormous library of previous webinars, educational videos on every topic under the many suns. You can find our library on YouTube by searching for our username, AAVSOHQ. And I think that's it. So to close, I would like to express one last heartfelt thank you to Shishir from all of us at the AAVSO. We appreciate you.
Thank you so much, and thank you for all your kind words, everyone.
And with that, thanks everyone for tuning in, and I'll see you all next time.